Hello everyone, welcome. This educational channel expounds topics in mathematics, civil engineering, and professional education subjects. This channel aims to simplify the lessons, and I am your founder, Bert, a Filipino licensed teacher and engineer. Thank you for watching.
Good day everyone. I will discuss the 9 basic solutions of differential equations. These 9 solutions are the one listed in lesson 1 to lesson 9. And our lesson 10 is the summary of the 9 different solutions of differential equation. And this time, we're going to take our lesson 1, separation of variables. This is the most basic solution among the 9 solutions, meaning the separation of variable is usually part of the other 8 solutions. Therefore, you should master this topic. But before we start discussing our first lesson, let us review our previous topics, including the symbols and notations used in our subject. In this way, we will have a common understanding with these symbols and notations. The letters A, B, and C are used to denote constant, while the other letters are used to denote variable, such as X and Y. For algebra expressions, AX denotes an algebra expression containing only variable X. 6 examples are given here. As shown, all expressions contain only variable X. Remember, these letters B, A, C, and another letter A are constant. For the notation AX, A can be denoted with other letters such as capital letter F, small letter f, capital letter G, small letter g. So, we can use capital letters or small letters. Yet, this module will usually use capital letter A for the functions that involves only variable x. How about when the letter x are changed to letter y? For the given 6 differential equations that contain only variable y, the notation is by. Again, the letter b in this notation can be represented with other capital or small letters such as f and g. However, we will be using by in our discussion. How about when the letters x and y are present in mathematical expressions? For such expressions, we will denote them with mxy or nxy. Examples are shown. The first examples is 3x plus 2y, so it contains x and y. The same is true in the other 5 examples. Similarly, the letters m or n in these notations can be changed to other letters, but we prefer the letter m and n in our discussion. I hope everything about the symbols and notations is clear. Now, let us connect our discussion on symbols and notations to the solutions of differential equations. Now let us classify differential equation into 2 cases. For case 1, the integrands can be directly integrated, meaning the integrand of dx should contain only variable x, or the integrand of dy should contain only a variable y. 3 examples for ax dx are given here. The first example, integral of x plus 1 dx and so on. For the example of integral by dy, we have integral of 1 minus sine y dy, integral of b plus ln y dy, and integral of 5 dy. For case 2, the integrands cannot be directly integrated and are denoted by integral of mxy dx or integral of nxy dy. Here, both of them contains variable x and y. Examples are provided. The first example, integral of x plus y dx. The same situations in other three examples that each contain variable x and y. Now, let us review the solution of differential equations. Example 1. Determine the general solution of 2x dx plus 3y squared dy equals 0. As noticed, the dx term contains only variable x. The dy terms contains only variable y. Hence, we can directly integrate both terms. So let's proceed writing the integral notation in each term. For easy integrations, the constant can be written outside the integral symbol. So let's write here 2 integral of x dx plus, let's write again 3 before the sign of integration, then y squared dy equals 0. After which, we call the basic integration formulas and the integration techniques. Which of these formulas and techniques are appropriate for these terms? Well, use power formula. The power formula is integral of un du is equal to un plus 1 over n plus 1 plus the constant c. Applying this power formula, we have 2, then apply power formula to integral of x dx, in which n here is equal to the exponent 1. So the answer is x 1 plus 1 over 1 plus 1. For the second term, write 3 here, then apply the power formula for the integral of y squared dy. N here is equivalent to 2. So, the answer is y 2 plus 1 over 2 plus 1. Then write constant here c. Simplify the terms inside the bracket. That would be the next step. So we have x squared over 2 plus 3, then y, you have 2 plus 1, that is now 3 over 3 equals to letter C. As noticed, the constant 2 can be cancelled. Also, the constant 3 are cancelled. The remaining or the simplified equation is x squared plus y cubed is equal to c. This is the answer. In conclusion, directly integrate the differential equation in the form of ex dx plus by dy equals 0. We can integrate this equation with the use of the basic integration formulas and the integration techniques. This direct integration process can be applied regardless of the number of terms as long as all the terms are in the form of ex dx and by dy. For illustration, Let's try 4 terms. Example 2. Determine the general solution of 2x dx plus 3y squared dy minus 3dx equals 4y dy. In these equations, there are 2 dx terms, the 2x dx and negative 3 dx. The remaining 2 terms are both dy terms. Obviously, all terms can be integrated directly. However, our primary concern here is to relate this given differential equation to the above equation 1. So in this part, before integrating, let's combine the dx terms and combine the dy terms. So I'm going to write here the 2x dx and negative 3 dx. Then the other 2 terms, we have 3y squared dy, and let's transpose 4y dy to the left side. So the sign becomes negative. So negative 4y dy, then equals 0. For the first 2 terms, the dx terms, let's factor the dx. And for the other 2 terms, let's factor the dy. Inside the parentheses here, for the dx term, we have 2x minus 3. And this 2x minus 3 is now the ax in equation 1. So ax dx plus, for the second term, the dy terms, inside the parentheses are 3y squared, then negative 4y. And this 3y squared minus 4y represent the by. So we have also here the dy, then equals to 0. This is now our equation 1. Therefore, we can directly integrate the differential equations of any number of terms, such as 4 terms, 5 terms, or more than 5 terms, as long as all the dx terms contain only variable x and all the dy terms contain only variable y. How about when the given differential equation is not in the form of equation 1? Well, one of the possible solution is the separation of variables. Now let us discuss our first lesson, the separation of variables. Our learning outcome, at the end of the lesson, the students will be able to find the solution of variable separable differential equations. We have here the steps in finding solution. This is the given differential equation, wherein the dx and the dy terms contain variable x and variable y. So both terms are not ready for integration. To solve this equation, we will convert this equation into this form. Here, the dx term contain only a variable x, while the dy term contain only a variable y. Then, the next step, integrate and simplify. Now let's take example 1. Obtain a general solution of x dy minus y dx equals 0. In this equation, we're going to transfer x to dx and likewise transfer y to dy. But how are we going to do that one? Okay, we have here the x dy minus the y dx equals to 0. To do that, we're going to multiply this by 1 over x. Where did I get x? X is now this variable. The purpose of this x is to cancel this x. Then, to cancel this y, I'm also going to place here y. Doing that, you have here x dy, then multiply 1 over xy minus y dx, and multiply by 1 over yxy equals to 0. Here you can cancel now x, so the remaining is dy over y, then minus, here you can cancel y, then you have dx over x is equal to 0. This time, the dy has only variable y and the dx has only variable x. Now we are going to integrate the terms in the equation. Integral of dy over y is ln of y. Then minus integral of dx over x is ln of x. Then equals, to add constant, you have ln of c. Then condense the left terms in the left side. We have ln of y over x, and that is equal to ln c. From this equation, we can have y over x is equal to c. Then multiply the whole equation by x, then we have y is equal to cx. And this is our final answer. As noticed in our solution, we use the symbol ln of c for our constant. Then the question, how about if we will use only letter c to represent the constant? Do we have the same answer? Well, we're going to try. So in this line, we will have here ln of y minus ln of x is equal to letter c only. Then we are going to condense the ln terms. We have here ln of y over x is equal to c. Then using the ln property, we have here y over x is equal to e raised to c. Then take note, our e raised to c is still a constant. Therefore, this can still be written as letter c. So we have here y over x is equal to c. So this is now our answer, which is equivalent to our previous answer. In conclusion, we can use any symbol for the constant. We can use ln of c or simply c. Then we can also include numerical coefficients such as 1/2. So we can use c over 2, or we can use trigonometric function such as sine of c, or any other symbols as long as there is no variable. At this time, I'm going to try this c over 2. So again, we have here ln of y minus ln of x is equal c over 2. And then we can condense now the terms in the left side. We have here ln of y over x is equal to c over 2. Then using the ln formula, we have y over x is equal to e c over 2. Then we have y over x is equal to, since this is only constant, we can use only letter c, and this is now our answer. Furthermore, the differential equation in example 1 can be written in many form. Example, we have dy over dx is equal to y over x. This given equation is equivalent to the given problem, therefore, the answer for this is the same to our previous answer. What I want to emphasize here, the dx here is in denominator. So, we have to write the dx in the numerator before you can integrate. So, we have here the dy over the dx is equal to y over x, then multiply this equation by dx. Doing this one, the dx is cancelled here, so you have the dy is equal to y dx is over x. So both dy and dx are now in numerator. Then you may proceed to place the y variable to the dy and likewise the x variable to the dx. In this situation, we will just multiply this one by 1 over y to cancel this y. So you have here dy over y is equal to dx over x. Instead, that dy over dx will be written here, we can write it into y prime is equal to y over x. Take note again, if you are given this equation, this is just equivalent to this number 1 form and to the original given. Or else, that equation 2 can also be written into x y prime is equal to y. So if you are given y prime in an equation, just substitute the value of y prime, which is dy over the dx. And that is now equal to y over x. Then you can proceed to solve the problem. Then, in this example 3 form, we can also substitute the value for y prime, that is dy over dx is equal to y. And for this form 3 and 4, you can just apply the methods that we have applied in form 1. And of these 3 forms, we should have the same answer. This is the end of our first part of the lecture. I hope you're able to follow the discussion, and for more examples, please proceed to the next video.